Great. We see a lot of people joining. So welcome to our very first hybrid Frontiers in Biostatistics seminar. My name is Erica Pike, and I am the program manager for the Department of Data Science. So we are very pleased to have Wendy London here today, but I'm going to, after a few short comments, I'm going to turn it over to our faculty organizer, Svetlana. So very quickly, obviously, if you're here in the room with us, you can just ask your questions. But for our virtual audience, you can put your questions in the Q&A, and we will be looking at those and making sure that we get them out to the presenters today. The chat is also open, and we'll be using that today during the talk as well, so keep an eye on that as well. And with that, I will turn it over to Svetlana.
Thank you very much. It's my great pleasure today to introduce two speakers. Dr. London, she's here with us in person, and Dr. Ma joining us from Canada. Dr. London is an associate professor of pediatrics at Harvard Medical School and the director of Biostatistics in the Division of Pediatric Hematology and Oncology at Dana-Farber Cancer Institute and Boston Children's Hospital. She is the director of BFHCC Server and Qualitative Methods Core. Dr. London completed her PhD in Biostatistics at the Virginia Commonwealth University, and she serves as a member of the Children's Oncology Group, Neuroblastoma Steering Committee, and was lead statistician for the Children's Oncology Group Neuroblastoma Committee. Dr. London chairs the Statistics Committee of the International Neuroblastoma Risk Groups Task Force, and her research focuses on pediatric solid tumors and specifically neuroblastoma. She is developing clinical trial designs, phase 1 and randomized phase 2 and 3 trials. She's interested in identification and application of prognostic factors, and she as well is interested in medical informatics, including data warehouse design and development. Dr. Ma is independent biostatistician and co-director of the Biostatistics Core Services at the Center for Addiction and Mental Health at the University of Toronto. He's an assistant professor of biostatistics at the University of Toronto, Dalai Lama School of Public Health. He completed his PhD and postdoctoral training in biostatistics at the University of Michigan. And prior to moving to Toronto, he was the lead biostatistician at the Dana-Farber Boston Children's Cancer and Blood Disorders Center and an assistant professor of pediatrics at Harvard Medical School. Dr. Ma's research focuses on developing and implementing innovative statistical methods to improve the accuracy and efficiency of clinical trials. He is developing new trial designs and also interested in implementations, and several of his novel designs were implemented in the clinical trials. And today our speakers will tell us about the design and implementation of Bayesian adaptive phase 1 trials in oncology using the DEDUCE application. Thank you very much.
Thank you, Svetlana. Thank you very much for that kind introduction. Thank you, Erica, for organizing this. We're very pleased to be here. I hope that today I may pique your interest in adaptive designs for phase 1s if you haven't used them before. And we hope that through the DEDUCE application, we can offer you a tool that might make it easier to begin to understand and to use adaptive designs. Okay, so I'm going to talk briefly about rule-based designs, and but the main focus will be on adaptive phase 1 designs. And we're going to show you 4 pediatric oncology trials that are ongoing using adaptive design phase 1 trials. And Clement will show us a demonstration, and you guys can do a hands-on with a link that'll be in the chat to try the DEDUCE application. It's short for Design and Conduct of Dose Escalation Trials. So today our focus will be limited to phase 1 trials that have an objective of determining the maximum tolerated dose, and the primary endpoint is the occurrence of dose-limiting toxicity. So of course there are other types of phase 1 trials with composite endpoints, but today our focus is only on DLT. So we observe a patient over 1 course or 2 courses as defined in the protocol, and it's a binary endpoint, occurrence of DLT or no DLT. So we make an assumption about the relationship of dose and the DLT rate, with increasing dose level, we assume that toxicity goes up. We're also assuming that hopefully the efficacy of the drug will be increasing. For the adaptive designs, the investigator gets to specify a limit above which a drug would be considered unsafe. In this example, the target toxicity threshold has been set to 30%, but investigators will sometimes pick something as low as 20%. So in a rule-based design, the protocol specifies a set of predetermined rules that are used to assign a patient's next dose level. Now, these are easy to implement and easy to understand, but they're really conservative in terms of safety. And this turns out to be a disadvantage because the dose escalation process can be slow. And at the end of the trial, many patients may have end up being treated at subtherapeutic doses. Rule-based designs are called memory lists because they only look at the current dose level to determine what to do, whether it's escalate to the next dose level, and ignores all the other patients treated at all the other dose levels. Many of you are very familiar with the 3+3. I'll just be very brief. You enroll the first 3 patients. If you have no DLTs, you can escalate. If you have 1 DLT, then you enroll an additional 3, and out of the total of 6, if you still only have 1, you can escalate. And otherwise, if you have more than 2 or more out of 3, or 2 or more out of 6, then you terminate the trial, and typically the previous dose level, the lower dose level, is considered the MTD. So we are using the MTD to make a decision about what dose level should be used in future studies. This can be called the recommended phase 2 dose. Often investigators will choose to enroll additional patients at this dose level, called an expansion cohort. This will give extra precision about the rate of toxicity and perhaps some preliminary information about efficacy. So the 3+3 has some inaccuracies and is conservative. So Alexia Iasonis did a very nice series of simulation studies published in Clinical Trials in 2008, and she showed that the true MTD was only identified in 1941% of the trials in the simulation study, as compared to a Bayesian adaptive method called the Continual Reassessment method, CRM, that can identify the MTD in 25 to 72% of trials. So as I said before, the 3+3 ends up treating fewer patients at higher, more effective doses. And the rolling 6 is a rule-based design that's very popular in pediatric oncology, and it has similar inaccuracies and it's similarly conservative. So according to FDA guidance, an adaptive clinical trial is defined as one that evaluates a treatment by observing the outcome, modifies the trial conduct in accordance with those observations. Now that sounds pretty subjective, but it's not. The protocol specifies every step of the way the adaptation schedule and the procedures to be followed. Adaptive trials can be phase 1, 2, or even 3 trials. So 2 of the methods we're going to talk about today are the CRM by John Quigley and the Boyne method, Bayesian optimum interval method, according to Ying Yuan. So Clement will also show us a couple of designs, his extensions of the CRM, the TARGET-CRM and the subtype CRM. So an important point I'd like to make is that any of these designs, including a 3+3, provide information for the investigators to make a decision about dose escalation or de-escalation. Statisticians and computers don't dictate how patients are treated, whether it's with a 3+3 or an adaptive design. Ultimately, these are just tools to inform the safe decisions that investigators make about changing the dose. So when you're considering your next phase 1 trial, I ask you to think about the possibility of having an adaptive design here, because conceptually, all phase 1 and 2 designs can be thought of as adaptive. So even a 3+3, you're using information to decide based on that dose level whether to go up. A phase 2 Simon's 2-stage design is adaptive. Based on the first stage, you decide whether or not to go to stage 2. So again, the statistical model is only a recommendation to the investigator. One of the drawbacks of an adaptive design is the need for real-time data for real-time decisions. And I say drawbacks because it just requires extra vigilance, time and effort, and cost. sometimes there's going to be more time required by the biostatisticians or the staff. So why should you do an adaptive design if it requires all this extra effort? Well, in the examples we're going to show you today, we needed these adaptive designs to resolve an unmet need or a challenge within a particular trial, and it really becomes worth it. So the first method I'd like to talk about is the CRM. And just in general overview, we're going to dive into the details in a minute. It uses a Bayesian framework, and it iteratively fits the dose toxicity curve using the prior specified by the investigator, plus the DLT observations for all the patients so far on the trial. And using these data, the posterior probability of the DLT is calculated at each dose level, and patients are assigned to the dose level that's associated with the prior the posterior probability closest to the target threshold that the investigator has selected. It's also possible to add additional safety monitoring roles. So once the accrual for the trial is finished, the MTD is the dose level that has a posterior probability of a DLT that's closest to the target toxicity rate. So here in our studies, we use an R package to run the CRM. And the R package uses this power model in describing the relationship between the probability of a DLT and the dose level. And so on the right, you can see some curves for various values of the parameter beta. And in this case, the investigator has selected a target toxicity threshold of 20%. And so an estimate, beta is estimated, and then the dose toxicity curve is plotted, and the MTD is the point where the curve crosses the target toxicity threshold. So this is the formula for calculating the expected value of beta based on the likelihood shown here. We're not going to go into any great detail, so I refer you to Goodman, the paper in Stats and Medicine in 1995, if you'd like to see more information about how this expected value has been derived.
Can I ask?
Yes.
What distribution is generally recommended for the higher distribution? It's not the trial.
I think it's a non-informative prior, but I think I would need to double check that. But thank you for your question. Here's an example that shows a study that has 5 dose levels. So at the lowest dose level, the investigator has taken an educated guess that a DLT rate at this level will be 5%. Now the investigators can use other phase 1 studies or even preclinical studies to make their educated guess about what the priors are. And unfortunately, the headers on this table I see are missing. So this just says dose, and this header should say the prior. And so this is just the, this is to inform the Bayesian model in calculating the dose level and the probability of DLT at each of the dose levels. And so this example shows a variety of the choices for beta, and the black line is what the investigator has chosen in this case. So let's talk about the steps that you would take in actually running the trial. So the CRM has flexibility in the number of patients in a cohort. So usually people pick 1, 2, or 3 patients in a cohort. And so we enroll that cohort of patients. We observe whether or not they have a DLT, and then calculate the posterior distribution based on the combination of the prior that the investigator has specified and the observed DLT information to date. So we use the expected value of beta to update that dose toxicity curve. And then the next cohort of patients get assigned to the dose level that has the posterior closest to the target toxicity rate. So the protocol will specify typically that the dose escalation may not skip dose levels. That would be, in most cases, considered unsafe to go up by more than one dose level at a time. And so typically that's what the protocol prescribes. On the other hand, from a safety standpoint, de-escalation permits skipping as many dose levels down as the investigator would choose to. So there are no power calculations per se to pick what the sample size is. The sample size is based on the level of precision that you want for the DLT rate. And also, the larger the sample size, of course, the more likely you are to pick an MTD that's actually the true MTD. And the deduced application that Clement will show will give you those kinds of operating characteristics to allow you to see how the sample size affects your ability to identify the true MTD. And the MTD identified in the trial is the dose level with the final posterior probability closest to the investigator's specified target toxicity rate. So let's go step by step through an example. So in this trial, we've got 4 dose levels. Here's the prior on the right. So the investigator has decided that dose level 1 has a 5% chance of a DLT and dose level 4 has a 30% chance of a DLT. And in this trial, the threshold has been set at 20%. The cohort size has been selected to be 1 patient, and the protocol says we're only going to go up 1 dose level at a time, and we can skip doses in de-escalation, but other than increasing 1 dose at a time, we're going to escalate to the dose with the posterior probability closest to the threshold, and our maximum accrual is 18 patients. So here we are at the top, no patients yet. Let's go to the first patient, and that patient doesn't have a DLT. So based on the prior, plus the fact that this 1 patient doesn't have a DLT, the model makes a recommendation to escalate to dose level 2. And that's, again, according to the rules of only going up 1 level at a time. So I'm going to go back and forth between the prior slide. So here's the original prior. And now with the added information of only just 1 patient, you can see that the new estimates of the probability, posterior probability of DLT at each dose level have gone down. So the investigator agrees with the model recommendation and decides to escalate to dose level 2. We enroll a second patient who also doesn't have a DLT. Again, you see that 1 patient, 0 DLTs plus the prior, and now 2 patients, neither of them with the DLT, and our estimates of DLT go down across all of the dose levels, not just the 1 dose level that the patient was treated on. So a recommendation to dose level 3. And again, even though 15% is closest to 20, we're only going to go up 1 at a time. And patient 3 has a DLT. So you'll see a dramatic increase just based on, so now we have 3 patients, 1 of whom has a DLT. So here we were, 2 patients, no DLTs, 3 patients, 1 DLT. And the posterior probabilities take a big jump based on the occurrence of this 1 DLT. So now I'm going to jump ahead to completion of the study after all 18 patients. And you can see here that dose level 3 had 19% posterior probability of a DLT, closest to the 20% threshold. So that's been identified as the MTD and is likely to be the investigator's choice as the recommended phase 2 dose for further study. So if you look at just dose level 3, we see that 2 out of 11 is 18.2%, and that's different from what the Bayesian DLT probability is. And that's mainly because the Bayesian calculation of the probability includes the original prior in addition to all of the observed data on these patients. So don't be alarmed if you end up with a Bayesian DLT probability, the difference from the frequentist calculation at that dose level. So now I'd like to show you some examples of ongoing trials in pediatric oncology. We'll talk about 4 of them. 2 of them use Clement's modification of the CRM called the TARGET-CRM. These are 2 studies of targeted therapies. And then Kathy Warren is using a Boyne design, and Karen Wright is using Clement's modification of the CRM called the 2S subtype. So the first trial I'd like to show you is led by Drs. Du Bois and Schulman. Clement designed the trial, and Paige Cow and I are the study statisticians. So the primary aim of the study is to determine the recommended phase 2 dose of a drug called aileron 6924, which is an MDMX/MDM2 inhibitor. So patients that are expected to benefit with this drug are the ones who have an MDM2, MDMX amplification or gain, a TET2 deletion or loss, or a PPM1D amplification or gain. And these patients are of great interest because we would expect them to be the most likely to respond to this targeted therapy. So for 2 reasons, it's really important never to turn away one of these patients and maximize their enrollment. We want the patient to have the opportunity to have access to a drug that might benefit them. And secondly, we want to be able to study these patients in combination with this particular inhibitor to get some preliminary data on efficacy, even though the main point of the trial is the dose escalation to identify the right dose. So all the other patients with refractory relapsed solid tumors of lymphoma are in cohort A, and cohort B is our rare cohort with mutations that are likely to benefit. So if we were conducting this trial using the 3+3, let's say we're at dose level 2 and we've got 3 patients that are being evaluated. So there's no slots available for this patient to enroll, and that's really problematic. We don't, as I said before, we don't want to turn this patient away. We want them to give the opportunity for access to the drug, but if they have to wait, they may urgently need other therapy, or they may have further disease progression that makes them ineligible, or they might die. So Dr. Ma has made this modification to allow the rare cohort B to enroll at 1 dose level below the current dose. And so this increases the number of cohort B patients that we can treat. The beauty of the CRM model is that it takes all of the data of all patients at all dose levels and includes it in the calculation each time we want to make a dose escalation decision. So this new TARGET-CRM prioritizes the enrollment of a particular patient subset, whoever they may be and however you choose to define that subset. So Clement and I have a manuscript in development.
So yeah, I want to maybe you could enroll the patient would be to dose level 2 instead of dose level 1.
It's possible, and that's another one that we're considering. So the investigator would have to be willing, from a safety standpoint, to enroll additional patients at that dose level. I mean, from a statistical standpoint, yeah, it's fine. But you know, the reason you're evaluating 3 patients at dose level 2, according to the like 3+3, is that you're not willing to enroll anybody more than that until you know it's safe.
Okay, yeah, thank you.
So as you can imagine, if a patient has a DLT, we want to use that information as quickly as possible to decide what we should do for the following patient and what dose level would be appropriate for that patient. So we temporarily halt the accrual. We get the data entered by the clinical research coordinator into the electronic case report forms. The statisticians run the updated model, now including this new DLT. They generate a report, which is reviewed by the study team. We make a decision about whether the dose should be escalated. And if escalation, the IRB has to approve that dose change here at Dana-Farber. And then if approved, the studies reopen and the sites are notified of what the new dose level is for future patients. So we accomplish this within a maximum of 6 business days. Often we're able to do it much more quickly, and we have like a 48-hour turnaround by thanks to the IRB. Compare this to a 3+3 design that could take 2 to 4 weeks waiting to determine what the next dose level should be. We have an additional targeted therapy trial that's also using the TARGET-CRM, similar circumstances as the aileron trial, and designed by Clement, and Paige and I are currently the statisticians. And then Dr. Kathy Warren has a trial for children with diffuse intrinsic pontine glioma, DIPG. And her challenge was a design that would allow her to test Morozumab alone, and then get the starting starting MTD before combining it with panobinostat. And she needed a design that was more flexible, and she wanted the increased accuracy over the 3+3. So she worked, before she came to Dana-Farber, she worked with Ying Yuan on this design. And so Nan Chen and I are the statisticians on this trial now here at Dana-Farber. And it uses the Boyne design to identify the MTD to be used for the recommended phase 2 dose. So this is the flow diagram that appears in the protocol, and based on the choice of 30% as the target toxicity level, these two thresholds were calculated below this threshold of DLT rate just by this simple formula. We would escalate the dose, and if above this threshold, we would de-escalate the dose. But it's all more simple than that to actually execute the trial, because all these calculations are done in advance. This table is agnostic to whatever dose level you're on. So this table was generated in advance of the trial. And so, for example, let's just say that at the current dose level, whatever that dose level is, we have 6 patients who have been treated. So if 1 or fewer patients has a DLT, then you can escalate. If 3 or more, de-escalate. And if 5 or more out of 6, and 4 or more out of 6, then we'll completely eliminate that dose from further consideration. So in the Boyne design, there is still need for rapidly communicating that a DLT has occurred or that the DLT period is over, so that you can determine the next dose, but you don't have the statisticians rerunning the model each time. You just refer to the table in the protocol. So the benefits of the Boyne is, again, as other adaptive designs, it allows you to choose how many patients you want to enroll in a cohort before you make a dose de-escalation or escalation decision. In this case, we had 3. Dr. Warren chose a fairly large sample size for a phase 1 trial. For pediatrics, it's usually a lot smaller than this. But again, increasing sample size will give you a higher chance of identifying the true MTD and greater precision in the final DLT rate estimate. Target toxicity rate was chosen at 30%, and we have, with the Boyne, it's more likely to select the MTD over the 3+3 with a lower risk of overdosing, and more patients have been shown to be allocated to the MTD than with the 3+3. I'd now like to pass the seminar over to Clement Ma, so that he can tell us about the next design and the next trial.
Thanks, Wendy, and thanks so much for the opportunity for us to present here today. So let me just share my screen really quickly. Great. So for the 4th example, this was another phase 1 trial, this time in low-grade gliomas. And the agent that we're investigating is called Day-101. It's a pan-RAF kinase inhibitor. The PI was Karen Wright, and Wendy and I were responsible for designing the study, and now Paige and Wendy are conducting the study. So our primary objective is the same. We're trying to determine the recommended phase 2 dose. Now the endpoint is slightly different. So here we have a time to event endpoint. So it's the DLT free time. So it's measured as the time from the beginning of treatment until the occurrence of a DLT. If there's no DLT, then it's the time from the start of the treatment to the end of cycle 1. Now, when we were thinking about the design of the study, there was the unmet challenge that we wanted to determine the recommended phase 2 dose stratified by 2 separate subgroups based on the patient's body surface area, BSA. So you can see here, there are kids who are smaller, a BSA less than 1.5 meters squared, and those who are bigger, a BSA greater than 1.5 meters squared. And we wanted separate estimation of MTDs for each subgroup. So why were we interested in this? So there was a initial trial with 9 patients conducted by the same group, and they had originally used the 3+3 design. The drug was well tolerated in that initial trial, but the investigators saw some of the PK data and noticed that potentially there would be differential response rates based on the BSA of the patient. So that's what prompted the investigators to consider a follow-up trial, now looking at estimating the MTD within each BSA subgroup. So the methods that we've described, 3+3, CRM, TARGET-CRM, they all implicitly assume that patients are relatively homogeneous, and we're going to estimate a single MTD for all the patients. Now, if there is patient heterogeneity, then it might be preferable to estimate subgroup-specific MTDs. And patients could differ on any number of aspects, demographics, clinical characteristics, or tumor type. So you can imagine, in a hypothetical setting, suppose that we have two subgroups of patients. These are the hypothetical dose toxicity curves, and you can see that the patients in subgroup 1 in red, they generally have a higher toxicity rate for the same dose compared to those in subgroup 2, and it's possible that a dose level 2 is the appropriate MTD for subgroup 1, whereas we can give a higher dose for patients in subgroup 2. So there have been a number of methods published that can do exactly this, try to estimate subgroup level MTDs. And one method that we were narrowing in on, it's called the subtype design, the subgroup specific time to event continual reassessment method. And this is a method published by Andrew Chappell and Peter Thal. The idea is that this uses a spike and slab prior and the DLT information to date to estimate the dose toxicity curve for each subgroup. There were three main features of the design. So one is that time to events endpoint. This allows us to include partial DLT observations as like the time to events or tight CRM design. And this allows more continuous patient enrollment without having to wait for the completion of the DLT observation period for the current cohort of patients. The second feature is what they call borrowing information across subgroups. So, and what in the original paper, they showed that by allowing borrowing across subgroups, this is more efficient than running simply separate trials for each subgroup. And then finally, they had a feature called dynamic clustering, where subgroups can be combined or split apart dynamically, depending on the current evidence, the dose toxicity curves estimated, whether they're more homogeneous or heterogeneous. And again, this has been shown to, again, improve the accuracy by reducing potentially the number of subgroups that are being estimated at any one time. So as we were thinking of the design using subtype for the Day 101 trial, in speaking with the investigators, there were two aspects of this original design that we were interested in modifying. So the first was that the borrowing and clustering in the original subtype, these features started at the beginning of the trial. And we were interested in looking at a more flexible framework where the borrowing and clustering feature could start at some pre-specified point in patient accrual. And the idea was that by allowing gathering more DLT information before allowing borrowing or clustering, this might help increase the accuracy of estimating true MTD. The second was more heuristic. So in the original trial, the authors proposed a more aggressive dose escalation rule where even after testing a single patient on a dose level, if the model suggests an escalation, that would be allowed. And for the pediatric oncologists, this was kind of probably too quick in terms of escalation. So we proposed a more conservative set of rules where we require at least 3 fully observed patients on the current highest dose before a dose escalation was allowed. So combining these modifications, we proposed a modification called, which we call the two-stage or subtype design, 2S subtype. So the idea again is we have stage 1 where we're essentially running 2 parallel tight CRM designs, one for each subgroup. And then at a pre-specified point in time where, let's say, we reach 33% of our target accrual, then we would initiate stage 2 where the borrowing and clustering features of the original subtype design would initiate. and that would go to the end of the trial. And we conducted an extensive simulation study trying to identify the optimal kind of parameters and kind of robustness compared of this design versus 3 control methods. And we were able to establish, kind of help inform the design of this study. So I just want to show you a quick snapshot of kind of what happens during the trial. So at the beginning of the trial, with Karen and the other investigators, we had selected a set of prior probabilities for toxicity. And you can see that there were 5 dose levels that we were testing, and here are the 2 subgroups. So we need to specify kind of 10 prior probabilities here in this grid. And from the outset, based on the preclinical data, there was the expectation that the kids with the higher BSA would have a higher toxicity rate, and that's kind of shown here in that in the prior values here. So every week we would update the data, run the model, and then we would again assign patients based on the dose level that was closest to the target toxicity rate for each subgroup. And then here's another snapshot of one of our weekly iterations. This was the posterior probabilities estimated by the model. You can see that they have somewhat differed from the original prior, and actually, and these kind of continuously update as we go along. So there's definitely the practical challenge of trying to maintain this real-time data entry, because our models require not only reporting DLT events, which are important, but also because we're using a time to event endpoint, we need to know that the additional follow-up time will also inform. So if a patient has gone another week without developing a DLT and they have a longer follow-up time, they have more partial information to contribute to the model, that is equally to capture as capturing a DLT event. So, in terms of the study, we were a multi-site study, so it was not really feasible to have true real-time data in this sense. So we had implemented a compromise. We had a weekly reporting structure. So on Tuesday, we would ask all the sites to enter the updated data into the case report forms. We would download this, and then the statistical team would run the model and create a report. And then on Thursday, we had a PI meeting where we would review the model, review the recommendations, and then decide what to do for the subsequent week. And you can see it's not perfect. If a DLT happened on Friday, we wouldn't change the model until the following week. But this is our kind of best way to maintain our sanity, but also try to be as up-to-date as possible. So here's the current status of the 4 trials that we described. So for the 2 designs using the TARGET-CRM, we're about maybe halfway through the target accrual, and the study duration 48 months, 40 months. It would appear long, but this is kind of reflecting the rarity of pediatric cancers, and it's quite challenging sometimes to recruit these children to the trials. For the Boyne design, after 4 patients, the trial was actually halted due to lack of drug supply. And then with the subtype design, that trial is actually completed, and after 45 months of accrual. So what we're hoping is that, we're showing that these designs are feasible. It does require extra work, but I think there's some benefits because they each will try to solve a design challenge that might not be possible using some of the traditional designs. So I think just to elaborate on that, we're not saying that every trial needs to use an adaptive design, but we want to encourage all of us to consider adaptive designs for our trials. And there might be cases where there is an advantage of using such a design. They do require more planning, more manpower, and more vigilance. And again, they require the real-time data submission, which is definitely a challenge for multi-site studies. But these types of designs, they offer more flexibility when you're trying to run your study. So you can modify the sample size, the cohort size. You can have different subgroups, as I shown previously. You could alter the target toxicity rates and also enrich for the enrollment of a rare cohort of participants. And these are just a subset of of possible reasons why you might need an adaptive design. And there are a number of other methods that are published with other benefits that you might consider. So finally, I'd like to talk about the Deduce app. And this really stemmed from the fact that, at least in pediatric oncology, when we started this work, there were very few examples of adaptive designs in phase 1 trials. And there was a systematic review that was conducted by Dassault, and they had reviewed 90 published phase 1 trials in children, and they looked at the trial design that was used in each of these trials. And as you can see, the majority of the trials used either the 3+3 design, which is the blue bars, or the rolling 6 design in orange bars, both of which are what we call rule-based designs. There are very few examples of the model-based CRM, or another model-based design is the EWOC design. So, this is definitely a big challenge. And, Wendy and I, we were really thinking of how can we encourage more investigators, more statisticians to conduct adaptive trials. And we identified several potential challenges, just additional complexity, the requirement for rapid reporting of data, software issues, and also maybe the designs are not really targeted for specific therapy types. And we came up with some different solutions. And today, I'm going to be focusing on this one where we want to solve the challenge of the lack of software that allows for head-to-head comparisons across different designs. So we have developed a web-based platform to do just that. So our overall objective for Deduce, which stands for Design and Conduct of Dose Escalation Trials, is to develop a web-based R-Shiny application to aid investigators and biostatisticians in designing and conducting phase 1 adaptive phase 1 trials. So here's a screenshot of the page, and I'm going to show a live demo at the end of this presentation. So there are two main modules in Deduce. The first is the design module, where users can specify different parameters and then compare the operating characteristics for different phase 1 designs using trial simulations, and then make an informed decision, selecting an optimal design that best fits the needs of their trial. And once investigators have picked an appropriate design for their trial, then we can use the second module, the Conduct tab, which allows users to implement the design. And this will run the Bayesian algorithms and then allow users to determine the recommended dose level each time a new patient enrolls. So currently we have 3 designs available on Deduce. These are the CRM, Target-CRM. And as a point of comparison, we also included the rule-based 3+3 design. And we're actively working on adding additional designs such as the rolling 6 and the Boyne design to this platform. And so some of the key features of Deduce include, again, that simultaneous comparison of multiple designs using the same set of simulation parameters. So it's a kind of a fair comparison. We also are able to dynamically generate a written report with tables, figures, and a written summary of the simulation results. And this will allow investigators to interpret the simulation results, as well as include some of these results in their protocol or reports to regulatory bodies. And then finally, we implemented we call a modular design, where we're hoping that new designs can be added as long as they adhere to certain kind of standardized inputs and outputs. And here is, I think, where we're hoping to also reach out to you, the statistical community, where if you have a design that you wish you wanted to use or you're very passionate about, we would love to chat with you and see how we can work with you to implement this and add it to this platform. So before I jump to the live demo, we wanted to just acknowledge the team at Boston Children's. And Nan Chen is our current statistician working on the development of the new features of Deduce. And then we worked for the past year and a half with philanthropic arm of Northwestern Mutual called Tech for Good. And their team had provided a pro bono kind of effort to develop the initial version of Deduce and provide project management and also graphical design support, and really appreciate all their support. And they have also provided additional funding for us to continue to develop Deduce and also provide educational opportunities such as what we're doing here today. And also we wanted to thank Alex's Lemonade Stand Foundation for additional support. So now I'm going to switch to the live demo. Let's see if I can pull it up. And I'm going to also put in the chat box the link to the Deduce app. So you're very welcome to try it out. Currently, we're on this kind of free version on our Shiny. So it limits the number of users actively kind of running the simulation at this time. So you might have to wait a little bit. But we're planning to move this platform to Amazon Web Services, where they're going to be hopefully more users will be allowed to use the app at the same time. So here again is the Deduce app. You can see on the top is the menu bar. This version is our in development version with a few additional features that are not yet available. We're still actively testing it, but I'm going to use this version so it doesn't interfere with anyone trying the link that I've submitted here. So I'm going to first start off with the design module here. So I'm going to click here. So users will first need to specify some parameters for their trial. They start off with which designs they're interested in comparing. So I'm going to just select all three here to show off compare all three. And then for the trial, they users have to specify how many dose levels are included. And this is a slider like this. I'm going to keep it at 4 dose levels. You can also provide a label for each dose level. And there's some built-in error checking. So if you try to just include 3 labels for a 4 dose level trial, it'll give you a little error message. Just add that back. You can specify which dose you want the trial to start on. So we're going to start at this dose level 1, which is actually not the lowest dose. And this is quite common to have a kind of a reserve dose in case we see some early DLTs. Now, for the simulations, you need to specify how many simulation replicates to perform. The more simulation replicates will increase the accuracy and precision of your operating characteristics, but also increase computational time. So for today's demonstration, I'm just going to keep it at 300 replicates just to reduce simulation time. But for your actual trial, we would recommend at least 1,000 replicates for each simulation scenario. Next, we need to specify the target toxicity rate. This is, again, the maximum acceptable rate of toxicity that investigators are willing to accept. So we're going to keep it at 20% here. Now, we need to specify the true toxicity rate for each dose level. This is our underlying truth. So because we're simulating data, we can specify this, and then that's how we're able to tell how often we're picking the correct dose. So here I've specified, for example, for dose level 1 here, there's a 5% chance of a DLT, 12%, 20%, and 30%. So relative to the target toxicity rate of 20%, you can see that dose 3, the third highest dose here, is the true MTD. That's what, we want the algorithm to pick this dose at the end of the trial. And we want to see how many times, how often we're able to pick this dose correctly. Next, we can specify some accrual kind of parameters. So how quickly patients will accrue, specify the average time between patient enrollments. We can specify the DLT observation period in days. So here, typically it's about 1 cycle of treatment. So anywhere between 21 to 28 days is pretty standard. For the Bayesian methods, we need to specify the prior toxicity probability. As we explained previously, that usually comes from the investigator based on preclinical or even prior clinical studies. And this can actually differ from the true probabilities here. So the closer your initial guess is to the truth, then you probably have a higher accuracy rate. But again, in a real trial, you don't know this. So this is our best guess. And then we can specify for the Bayesian methods again, the maximum sample size. So here I've kept it at 18. The 3+3 design doesn't have a maximum sample size per se. You just kind of follow the rules, and the study will end at whenever that first set of 2 DLTs occur, or if you reach the highest dose. We can change the cohort size. It doesn't have to be 3. You can recruit cohorts of 1 or 2, or even larger cohorts. For the target CRM design, we need to specify in their population what proportion of patients belong to cohort B. So here, these are our histologic or genotypic enrichment cohorts. These are patients who might be more likely to respond to your targeted treatment. So I've kept it at 10% here. So I'm going to specify all these parameters. I'm going to just click simulate here. This will take maybe a couple seconds to run. And again, as you increase the number of replicates, this will increase the computational time. And if you have a chance to try out the app, we would really welcome any feedback about the app, things you liked, things you didn't like, features that you wish were available. That we really wanted to kind of start the conversation with all of you. So here are the results. We can see there's 4 main metrics that we've plotted here. On the top left is a metric of accuracy. So this is how often in our 300 simulation replicates, we pick the true MTD, which again, if you remember, based on the target toxicity rate, this is actually this dose level 2 here. So you can see that it's bolded. The 3+3 design and the target CRM design seems to be about the same in terms of accuracy. And the CRM method has a slightly lower accuracy in this particular iteration. Again, I think with the higher replicates, we will get a better estimate, but you can see this is a way to compare accuracy. The second metric is how often we assign participants to each dose level. Ideally, we want to assign participants at or close to the target, maximum tolerated dose, and we want to limit the accrual of participants at doses above the MTD, which may be overly toxic. So you can see it looks like 3+3 design does a pretty good job of assigning patients at the MTD dose 2, but it also ends up overshooting a bit and assigning patients, more patients at dose level 3. Next, we can look at another metric of safety. What proportion of patients experience a DLT at each dose level? And you can see all these toxicity rates are well below our maximum acceptable rate of 20%. So I think this looks okay. The design looks okay here. And then finally, we're looking at the duration of the study in days. And here, the 3+3 design, it runs a bit faster because on average, doesn't require 18 patients to accrue because it could end earlier than 18 patients, whereas the CRM and target CRM design, that was one of the input parameters to require 18 patients. So that's that's why it requires a little bit longer study duration. And you wouldn't just, if you're designing a real trial, you would probably consider a variety of different true toxicity probability vectors to look at, in different scenarios, what would happen to the different designs for you to make an informed choice based on across all of these scenarios. There's also this downloadable report that I've alluded to. So this is this button here. I'm just going to download a quick report to show you very briefly. So just opening this up. So here you can see there's a full written report with the methods and then a written summary of the how to interpret the results. All the plots that you've seen are listed here, as well as a summary table with all the metrics in numeric form. So if you wanted to do additional plotting or kind of report it in your own way, users can do so with these numbers here. So I'm just going to go back. Finally, I want to show the conduct tab. So this is after you've picked your desired design. Let's say we're going to run a CRM model, and you can see a lot of the inputs here are the same as the previous tab, the design tab. Here you're going to be entering your patient data one by one. So let's say we're going to add one patient. This patient's given dose level 1. They didn't have a DLT, and we're going to include that patient in the model. Here we've the cohort size is 3, so you can see there's 2 slots remaining out of the 3 cohort of 3, and then we can run the model, and this will give us a table with the posterior probabilities. Here's the data, so we have that one patient here on dose level 1. with no DLTs. This was our prior that we specified. And the recommendation is actually to stay at dose level 1 because we haven't completed a cohort of 3. So we're not allowed to escalate. So suppose that we add 2 more patients here. Now we've completed our cohort. We're going to change this to no slots remaining. And then we rerun the model. You can see now the data has been updated. There's 3 patients with no DLTs. The posterior probability is very low and it's reduced. And the recommendation is to escalate to the next higher dose because this dose level, the 4.5%, is safe and well below the target toxicity rate of 20%. And similarly, there's a downloadable report, which I'll kind of show very quickly. And you can see it shows the observed data, that toxicity table, and some of the parameters and settings that have been used to estimate the DLT, the probability. So this is a report that we use to send updates to the IRB so that we have a very systematic way of reporting these events. So that's it. Thanks very much for your attention. I think Wendy and I would be very happy to take questions at this time.
Question for the implementation. So if I don't run cohort B, is it just proper to say 0 and it will, right?
Yeah.
Okay.
If I'm understanding, so if you just have 1 cohort of patients, then you could just run the standard CRM design, and you don't need to click the target CRM design because the 2 designs are the same except for the fact that the target CRM can have that additional accrual during the DLT observation period for cohort B patients. So yeah, you can set it to 0 or you can just not click target CRM. Both would be equivalent.
We have a question from the chat from Ransom J. He said, thank you, Wendy and Clement. Can you describe your experience with various reviewers, IRB, sites, and various stakeholders for modeling multiple groups in phase 1 and prior probabilities?
So our experience has been with the Dana-Farber IRB, and we haven't gotten a lot of questions because I don't think that there's been a lot of use or understanding of these kind of adaptive designs here at Dana-Farber. So I'd love to have more questions. And I appreciate that the IRB has permitted us to conduct these designs, but we haven't really received a lot of feedback, or we haven't had concerns. And the good thing is we haven't had problems in conducting designs. So we appreciate the IRB's acceptance of our ability to conduct these designs.
There are a lot of adaptive trials going on as Farber, or not too much?
No. And I think that compared to other leading cancer centers in the country, that we're probably behind the curve. If you look at, MD Anderson, I think of them as being one of the leaders in the country in adaptive designs. And so, I don't by any means consider myself an expert, but I do have these 4. Now we got 5, we got a couple more design. We have done these trials. We do have some experience with it, and would love to work with other people and have more adaptive designs here at Dana-Farber.
I gotta go. Do you have a budget template that would outline the resources that are required for these various trial designs? Because that's going to be a critical part to appropriately resource the statistician time for the different designs and get our investigators to build that into the budgets for the trials. And to convince everyone else that we need that level of biostat budget.
Yes, that's a great idea. And I think now that we've done 4 of these trials, that I have enough information on the resources that it's taken, that we could put in some good estimates depending on the choices. And so, like the Deduce app, you're comparing the operating characteristics. I think that cost has got to enter into people's decisions about what's the best design for this trial.
That would be awesome because you have your different experiences now about meeting regularly, meeting, weekly, meeting at the end of each cohort. Yeah, that'd be really nice.
Yes, great idea.
Very nice. Thank you.
So I had a question. We've run a couple of these kind of we've done Bowen mostly, and then also Bowen combination designs. And so the combination I don't think we've gotten through the IRB yet. I think we're still waiting on that one, but we're moving forward on these kind of designs in the women's cancers. And so one of the questions that comes up, and I actually haven't been able to have, I would guess, a very good answer, so I'm hoping maybe you guys can point me in the right direction, is sometimes they want to be able to have the flexibility to change the number of dose levels they're exploring. So, sometimes they want to be able to say, especially in the combinations, where they're thinking about, okay, they think they know what they want for the one drug, but the other drug they want to explore. But then maybe if none of those work out, they want to add a couple more levels where they change the other drug level. So I don't know, like so far we've kind of fudged it and we've got it like NCI-CTEP has been okay with them kind of like saying that we'll go back and we'll do it. And the operating characteristics that we're presenting are a bit conservative because they look at more dose levels than probably we're going to look at. But I was wondering whether you have any experience with these and whether there's any suggestions for like with these adaptive designs, is dose levels, the number of dose levels you're exploring something that you can modify as the trial is ongoing?
So we have done that for 2 of the CRM designs. We have the target CRMs. We've had actually to go lower because at the starting dose, we had more toxicity than was anticipated by the investigators. And so these additional dose levels have been added. Clement, you can give your opinion here, but I think it's fine because the CRM is able to take into account all of the dose levels in all of the patients. And that's all encompassed in the modeling because of its flexibility. And even the Bowen design, that table is agnostic to the dose level. And it just tells you based on your pre-specified, probably your threshold of a DLT, what are you going to do at that dose level that you're currently on, and allows you to explore other dose levels without regard to how many there are. What do you think?
Yeah, no, that's good. I think when we had to add dose levels for the aileron in the BMS trial, we went back to the design phase where we did additional simulations with, I think we added 2 additional dose levels, which were interspersed in between dose level 1 and dose level -1. So we had to do additional simulation to demonstrate that our accuracy wasn't hugely impacted by adding these lower dose levels. Do we have to increase the sample size? So kind of justify statistically what might happen. But you're right, these trials might not go the way you plan, and there definitely you might need to add dose levels. If you already anticipate that you might do this, you might consider writing it in, like as a future kind of, or a decision point potentially. If something happens, then we might add these 3 dose levels, and then it's more pre-specified. You could already run simulations to demonstrate what might happen in either case, and that will prevent maybe future critiques like, are you just making ad hoc changes? So that could be one way to handle it.
We actually have another seminar that's waiting to come into the room, so we're going to wrap this up. So thank you everybody for attending. See you all next month.